Now, since now you know something about merging meshes and MPC constraints, I would like you to try out an example to see if you can actually work with it, apply it and see if you understand it or not. So what we're going to do is, in this week's practice problem, we are going to consider a simply supported stiffened plate. It's a very classical problem. I've used it also previously in this same course, and also otherwise it's present for every software package actually. So if you have a certain plate, just a thin plate, so we are using thin shells here, and these shells are actually reinforced by means of beams that are I-beams. So you will see I-beams over the entire length, a few of them in the example problem. The example problem is of course given in the form of a PDF as well. So there are these repeating units of I-beams. I'm not going to draw it all of them, but there are five stiffeners that are placed on a thin shell. This shell is, there are some characteristics. It is simply supported on the four vertices. That means you want to simply support them here, all these locations. And I hope you know what it means by being simply supported. We make assumptions that the stiffeners have been bonded to the plate, which means that between the plate and the stiffener there is a perfect bond line. If this is your stiffener, this is your plate, there is a perfect bond line in between. The plate will be used as a shell and the stiffener is a beam in terms of idealization. So what you want to create is that a 1D beam model for a stiffener, and then multiply it 5 times, place them over a shell, which is a 2D shell. Now this is a 2D shell, but it's not planar. That means you need to create a 3D part to make a 2D shell on it, okay, which has a certain thickness, a standard section shell. What you need to be very careful about is that the centroid of the plate and the centroid of the beam are completely different from each other. So you need to make sure you apply the correct offsets as we have discussed before. When you create these certain sections, then make sure to join these parts together. You use tie constraints. These are another word for multi-point constraints. There's a special kind of multi-point constraints which basically work as rigid links. This you will find in Abaqus. Well, I should talk about Abaqus after a little while. So what I want you to do is I want you to work out this particular practice problem step by step by first creating the beam. You already know how to make a profile, apply a beam orientation to a part, etc. Then make a plate. In the assembly, put all of this together. And in Patran, of course, you work at the same assembly section. So there's no assembly and part, but you have to make the same part 5 times and then put it on the shell. And then you have to tie them together by means of tie constraints. And you will have a pressure load which is acting on it, a uniform pressure load across the entire plate, and the value has already been given in the practice problem assigned practice problem sheet. You also have all the dimensions. Dimensions are in inches. The pressure is in PSI. The properties are also in KSI. And work out this problem and see if you can get yourself to understand tie constraints by means of this particular example. Now there are certain rules that you have to follow while creating these tie constraints. Okay, tie rules. Now there are always going to be master-slave relation. In tie constraints, what you do is you apply the first method, that is the master-slave relation. And master-slave relation means that you have to make sure that one of the parts is considered as a master and the other part is considered as a slave. In general, right now, you have similar stiffness of both the parts because the materials are the same. But if you have different kinds of material properties, then you have to make sure that the master is much more stiffer than the slave. This is a rule. Second rule is that the meshes or element size, I'm going to write it as element edge length because it's obviously at an interface, should not be too far from each other. So if you use one element edge length to be that wide and you have so many nodes in between for the other part, this is absolutely wrong and it's not going to work out, because it wants to make a relation with every node that is present. And all these nodes basically have the same two nodes to be related to. So it's not going to be a good approximation at all. So you shouldn't keep the element edge length to be too far from each other on both the parts that are being joined together. Okay, so these are just some basic rules I wanted to tell you. There are more rules, and of course I want you to learn by practice. So start working on the practice assignment, and I will also have the assignment solved for both Patra and Nastran and for Abacus. So first I want you to work this out, and then by the end of next week or this week I will put up the results as well.